righty. All right, so introduction to engines. This is going to be kind of like an overview, a little bit of a preview of what we got going on for the next right around 7 weeks. Okay, so engines is another fast one. We're just going to be going full speed. It might actually be 6 weeks. Five. It's only 6 weeks. Yeah, so we got 6 weeks to crank through engines. Be a lot of material. All right, so first things first. 22-to-1 compression. Right, really high compression. You ever try to jump start a diesel? You can't do it with like the little jumper. You buy the little lithium ion pack and it jump starts all these gasoline. Try that on a diesel. It's going to be like, nope. Actually, I'll tell you the noise it makes. You ready? Beep, 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 beep. It's like freaked out. It's like, I'm done. So I had one of those from Costco. I tried to jump start a tractor. That little jumper never worked right again. Never again. And it's not even a big tractor. It was a small tractor, but it's a 20-to-1 engine. So those diesels have big batteries, bigger cables, bigger starters, because you actually have to build a lot more compression to get it started, okay? That's the overall. Now, if we were to just look at the compression, look at the combustion beginning with spark, this isn't intake, compression, exhaust. That's the next screen, which there's a great video on that too. The spark occurs right there, all right? So there's quite a few things that have had to happen before that point. But once the spark occurs, that is spark ignition. It started with the spark. Makes sense? And then the flame starts to come down, it builds pressure, and it pushes the piston down. So, you know, that's the only stroke that we really benefit from on a 4-stroke spark ignition, or really any 4-stroke engine, right? Now, yes, we have to do some of these next steps. Right? The intake, the compression, the power, and the exhaust. We have to do these 3, but the only one we really benefit from is the power stroke. Well, here's why. I'll explain to you. On the intake stroke, is that piston giving us any power? No. On the compression stroke, is it giving us any power? No, in fact, it's taking a lot of power because we're having to push it up. So we're like, man, this sucks. We have to do a lot of work. And then a beautiful thing happens, people. A beautiful thing. We give it a little bit of spark, and because there's already fuel in there, right, then it initiates combustion, right? Yeah, that's on the back of some bumper stickers and some t-shirts, so we'll come back to that. It starts this combustion, and as that air and fuel are burning, it's expanding, right? It's building pressure. So as it builds pressure, what's it going to do to the piston? Push it down. Right there, we can harness that power and put it into the crankshaft and have the crankshaft turn a transmission, have the transmission turn the drive shaft, have the drive shaft turn the wheels. We're getting power right there. Then, unfortunately, when the piston comes back down, that gas, that air and gasoline is now spent, so it's like inert. We call that inert. It means you can't burn it again. We have to exhaust it. Make sense? So you do the intake, the compression, and the exhaust. All are necessary just so we can get the power. Make sense? Power is the only one that actually gives us any zoom zoom. That's where the vroom vroom come from. All right, so if we review those just a little bit. Intake, sucking air in. Cool. Compression, squeezing it. Yeah, compressing it. Power starts with ignition unless it's a diesel, in which case the diesel still works like this. It just doesn't have a spark. It just makes so much compression. And then, to be honest, truly a more modern diesel, like even a remotely modern diesel, actually what it's going to do is it's going to get to that top dead center of compression, which we'll come back to. It's going to spray the fuel in time. It's going to spray the fuel at the correct time. And that's actually going to start the combustion, but it's still not started by spark, right? And then that gives us our power stroke, the beautiful thing. And then we have the exhaust stroke just to get all out the tailpipe. So a few details. You'll notice we got an intake valve and it's open on intake. In compression, both valves are closed. In power, both valves are closed. And then in exhaust, the exhaust valve is open. We got to talk about all of how those are open, why they're open, what happens when they're open, what makes them open, what makes them close, right? We got a lot of stuff to talk about with that. But that's the overall. Cool. And then like when you really get into engines, you know, so when they go to design these engines, there's a lot of research that's done. That's not really what technicians do. That's not like, I don't do that. So if you even gave me an engine right now and you were like, hey, we want to have this make more power, like about the only thing I could do is look at it and know if we can have more airflow in and or more airflow out, that means we can probably justify spraying a little bit more fuel, right? And if I spray a little bit more fuel, now you guys all know where's the actual power come from, where's the source? The combustion, but the actual energy is stored in something. The dinosaur juice, what'd you say? The gasolina? I know what's wrong with it. Right, so the only way we make more power is if we throw more gas. You can't just throw more gas. You gotta increase the airflow. You know, you can make it a little bit more efficient maybe by like increasing the compression. There's these little things we can do, but like technicians, we don't do all of this here. When we're talking about engines operate according to unchanging laws of physics and thermodynamics, we're not just like, oh yeah, let me bust out my book on thermodynamics real quick. That was mostly written by Albert Einstein and be like, yeah, that's right. Back when me and Al were talking, like that's not really what we do. You know, that's engineers do that. We could tweak it a little bit. One of the ways we'll tweak it, it's a fun time to bring this into this right here. One of the ways we'll tweak it, who knows what this is? Yeah, so we have an exhaust manifold from the factory. We can get a header that's got equal length tubes, better flowing maybe, right? Why might this add power right here? Right, if we have less restriction on the exhaust, we can get more airflow. That technically doesn't add the power though. But if we have that, what could we do? Add more fuel. And if you add more fuel, remember the actual energy is contained in the gasoline. So the gasoline is a hydrocarbon. When we combust that, we're essentially breaking the chemical bonds apart. When we break the chemical bonds, it releases energy. The more chemical bonds we break, the more energy. So in other words, the more gas we put in, the more power we get out. Make sense? Ratseni, go ahead. Yes, and I want to keep it fairly tight to just engines, but engines is one class and engine performance is a totally different class. But I'll give you these little pieces to help you be ready for engine performance. I don't think anybody has any business trying to study engine performance if they haven't done engine repair first. So yes, if you were to just add more fuel to the same amount of air, it's going to be too rich. In other words, too much gas and not enough fuel. And you can get a little bit of power that way, but pretty quickly it actually starts robbing power, right? So a stock vehicle, you could run it through the tuner and be like, hey, I don't want 14.7 to 1, which is not what they're doing from the factory on wide open throttle anyway. Most of them are trying to target like 13 maybe. You could say, hey, I want 12.6 to 1. And you could actually see a small increase in power. But the main way the tuner is going to give you a better stock power is they're actually going to advance the timing. If you advance the timing and you richen it up a little bit, you can get some decent horsepower gains without adding any more airflow. However, you're burning more gas, so your fuel economy just went down. And when you advance the timing, as we'll get into in the ignition slide in a little bit, you start to run on the borderline of damaging, right? So you want to advance it, but if you advance it too much, you're damaging the engine. You guys have heard like a bad tune blew the engine up, right? If you advance it too far, you kill it. So from the manufacturer standpoint, they'd rather be like, oh, the line of the max is right there. We're going to take 2 steps back and run right here. Because if they start blowing up engines because they were too close to the line, it costs a lot of money. So they're good to lose 5, 10 horsepower to make it a little more reliable. Make sense? So when we really get into that, you really cross over from engine repair, A1, into engine performance, A8, right? But I'll still give you little pieces to help you start to make the connections. Cool? All right, so as we do this, valves and ports in the engine cylinder head provide a means of sealing the combustion chamber. So there's a key word right there, sealing. Everything we're talking about with the engine, it has to do with like building compression, sealing. So if we have air leaking out the intake valve when it should be sealed, that's a problem. If we have air leaking out the exhaust valve when it should be sealed, that's a problem. If the piston comes up and we're expecting those rings to more or less seal the cylinder and they're leaking, that's a problem, right? So a big part of what we do in A1 is determine, is the engine doing its job? So if you have a cylinder and it's not firing, like let's say a misfire, right? You got a 4-cylinder and cylinder 2 is not firing. It could be the injector. It could be the coil. It could be the spark plug. It could be the wires going to the injector. It could be the wires going to the coil. It could be like all these things, right? So the DIY person is going to be like, yeah, well, the first thing I do is replace the spark plugs. And I'm kind of like, you have no idea if it's a spark plug issue. You don't, right? So the way I want you guys to know is, how do we do process of elimination? In A1, we don't do a ton with spark plugs. We don't do a ton with injectors. But what we do is compression, right? So there's 3 things an engine needs to fire. It's compression, fuel, spark, right? Now, when we say compression, it's kind of like compression and air, right? So it needs compression, air, fuel, it needs spark. You're going to throw spark plugs on it. Do you even know if it has spark? See what I'm saying? So spark and fuel, we'll talk a little, but mostly that's not really for A1, that's A8. So we come back to A1. We need air/compression. The reason I focus mostly on compression is because it needs air. Like, yeah, I got that, but that's pretty easy. Like is it not getting air would be as simple as just making sure that I don't know, your air filter would have to be so clogged, I'm not even sure humanly possible to get no air, but you do still have to consider the air tract. Mainly we're looking at compression. So when we were back on that page, when we showed the intake, compression, power, exhaust, if you don't make compression, you're not going to get a power stroke. Cool. Why don't you make compression? I don't know. Maybe it's got a leak at the intake valve, maybe a leak at the exhaust valve, maybe a leak at the head gasket, maybe a leak at the piston rings because they're worn. Maybe the cylinder's worn. Maybe there's a hole in the piston, right? There's all these possibilities. What we're going to focus on is the engine sealing, the engine making compression. Not that much on spark and fuel. Okay, does that make sense? All right, cool. Then, of course, if the valves leak, like it's saying, the pressure in the cylinder will not rise as it should during the compression stroke of the piston. If there's too little pressure squeezing the air fuel together in the cylinder, there's going to be either less engine power or maybe even no combustion at all. That's a full-on misfire. Make sense? So the sealing and these valves and the piston and the cylinder and all that stuff is really important when it comes to making that power stroke, especially when we're looking at how much compression it makes, okay? So that's the main deal. And then pressure and temperature we talked about. The Charles law, the more pressure you have, the higher temperature you have. So one of the things we need to do to start that ignition process is the combustion process or the ignition process is we need to raise the temperature. How do we raise the temperature with the compression stroke? We raise the compression, right? We squeeze it from 10 parts down to 1 parts. And if we successfully squeeze it from 10 parts down to 1 part, it's hot. All those molecules are agitated and they're like, get off me, you know, and what's it going to take until it all breaks loose? It's 1 little spark, boom, and everything's ready. But if you have no compression and you just spray a little fuel in there and you kind of like give it some like little and it's not really under a lot of compression, you could spark it. It's not gonna make any combustion. Make sense? You need a lot of compression. You have to. You need the compression that it calls for in the service manual, as a matter of fact. Make sense? That's why we check that. Cool. And then this is just kind of illustrating, same type of thing. If we push down on this, increase the pressure, it's going to increase the temperature. If we pull up on this, it's going to decrease the pressure and it's going to decrease the temperature. All right. If we heat it, it's going to increase the temperature and it's going to increase the pressure. And if we cool it, it's going to decrease the temperature and decrease the pressure, right? It's a lot of ways to explain the same thing. If your temperature's up, your pressure's up. If your pressure's up, your temperature's up, right? They go together. They have this relationship. Cool? All right. And so overall, that's kind of what we're trying to get at. And then when we look into like some more of the engineering aspects, they know the temperature of the gas is one measure of how much energy it has. Okay. Heating of a gas, particles make them move faster. So we're going to heat it, and that's going to make them move a little bit faster. And that's going to make them even more prone to that combustion process, like I was kind of saying. Cool. How do we do it? We raise it first by doing compression of the air and fuel mixture, right? And the more compression we give it, if you look, this was kind of interesting. The more energy the air fuel mixture has, the more force it exerts on the piston and the more work it can do. It's kind of interesting. When we run the higher compression, it's going to have everything even just squeezed a lot tighter, more volatile, more ready to start that combustion process. And it's going to be more likely that we're going to have a thorough and complete combustion. Make sense? If you're running an 8-to-1 compression, that's enough to fire the cylinder, but there might be a little bit of fuel left over. You know, it might not really start the combustion process exactly when you were hoping, right? So by increasing that from 8-to-1 all the way to like 10-to-1, 10.5-to-1, anybody know what a performance engine makes? What do we got on the GR Corolla? Anybody know? It's up there. I don't think maybe it sounds a little high, but as you start to get over those 10-to-1s, 10.5, 11-to-1, 12-to-1 maybe, that's a very efficient and very powerful compression ratio. Make sense? So I just listed all the positives, right? It's going to be more efficient because you're going to thoroughly burn all the fuel. It's going to make more power because you're thoroughly burning more fuel. If any fuel's left over, that's lost power, right? What's the negative of the higher compression? Well, actually, let me back up. That was a good point. I just thought of something that makes a lot of sense. Let's say that we spray, I don't know, let's do it in drops. We spray 100 drops of fuel. There's a potential for all 100 drops of fuel to burn and make this much power. 100 drops of fuel equals 100 horsepower. How about that? If we spray 100 drops of fuel, we get 100 horsepower. Cool? Okay. And if we don't have high enough compression and we spray 100 drops of fuel, but only 90 drops of fuel are burned, how much horsepower do we make? Probably only 90. But are we getting better fuel economy? No, because we already sprayed the 100 drops. Make sense? So like what you guys were thinking, the negative of high compression is not actually a loss in fuel economy. The higher compression means it's going to burn everything we sprayed. So it can actually be an increase in fuel economy, believe it or not. That kind of crazy. So the new engines have higher compression, yes, for power, but also for efficiency. But, right, because if we spray 100, we want to burn 100. You don't want anything left over, and the higher compression helps with that. But there's still a big problem. What is it? More heat, more pressure. Why is that a problem for our engine? More heat, more pressure. It's harder. You got to have harder parts, stronger parts. Now you're starting to say like, well, we can't just run like some cast pistons and rods. We need to start getting into some forged stuff. We can't be running some janky cork head gasket. We need a multi-layer steel head gasket, you know, like, and if you're going to run higher compression, it's higher pressure, right? But it's also higher temperature. So now you're putting more load on the cooling system. You need a bigger radiator. You need a higher flow water pump. Like all good things, more money, more problems, maybe, right? More failures, more potential blew the cookies out the bottom of the oil pan type of thing. But they're better, they're more efficient. It's a lot of good things, but they're not as cheap as they were. Go ahead. Uh-huh. All right. It's a fair question. You're trying to pull me into A8, but I'll take 2 steps into A8 and then I'm gonna back out of it. The air fuel ratio is not adjustable by you, the technician, because that's set by the manufacturer, certified by the government, and then it's sealed off and you're done. That car was approved to whatever, I don't know, NZEV, near zero emissions vehicle or whatever. US EPA, this certification, calibration, or whatever, if it's lower, you know, if let's just say it's if you start to make it run more rich and modify emissions and stuff, it's no longer a near zero emissions. It may be like a ultra low emissions. You just reclassified the whole emissions certification. You know, companies who have, I'm sorry, we'll call it how it is, Dodge. Dodge, you think they're an efficient company? They're like Hellcat, you know, Scat Pack, you know, put a V8 in a minivan just because, you know, that's kind of they get down. At the end of the year, they actually pay fines and credits for not being as efficient and as low in fuel economy as they're supposed to be set by the federal government, okay? So that's way above our pay grade. And if you're doing it, you're breaking the law. Depending on what state you're in, people care or they don't care. But I'm just letting you know, you're not supposed to be adjusting that. That's why TIS, TechStream, GTS Plus, Snap-on, Mac, Matco, whatever. You pick the scan tool, Innova, I don't care. You can't, that's not part of their program. Now you go ahead and you buy HP tuners and you pay a fee to crack the ECM, pull the code, and then you could start rewriting stuff. Yes, but you're not operating as a technician anymore. Now you're tuning stuff, and not for the manufacturer, you're not. That's like your own independent shop. Sure, go for it. All right, I'm done with A8. We're back to A1. All right, cool. Same with on A1, if you increase the compression, you can start playing with the ignition timing. You can start playing with the air-fuel ratio as a result of the headers, as a result of the cold air intake, right? A1, we're focused on the engine and its ability to breathe and its ability to seal. And if you do all these improvements, you make it breathe better. Yeah, it probably really needs to be tuned to be correct, to be, to be right. You might be able to get a little bit. It to an extent, it does do minimal adjustments on its own. Also A8. Cool. All right, so as we go more into it, we kind of talk about this a little bit excessively. Again, we're bringing this up, and when we get it to the top, we're going to call it out right there. That's our top dead center. Top dead center should be the highest compression we're going to make. That's the point where everything is just ready to start combustion, ready to burn. Bang, spark it, and then that fuel is going to expand, and then that's going to start to push back down. Cool. So that's what we're trying to do. All right. And then if we look at this, just so you know, gasoline has a BTU per gallon. So there's a certain amount of power that can be extracted from gasoline. So if you had everything dialed in perfect, very, very efficient, you're spraying 100 drops of fuel, 100 drops are being burned, you can get 14,000 British thermal units as a maximum from gasoline. Make sense? Who thinks diesels make more power than gas? I mean, it kind of just in general. So we could say horsepower or torque. And we'll get into horsepower versus torque. I'll help clarify it. But as fuel for fuel, look at this. Diesel has 25,000 BTUs per gallon. Gasoline only has 14,000. And that's kind of the thing. So if right there you accept the fact that diesel has more energy in it, there's higher potential for power out of diesel. There just is. Sorry. Comes with a cost though. There's a lot of challenges with that. Again, diesels are running much higher compression, like double the compression. Remember what we talked about. You increase the compression, what's the negative? Everything's got to be stronger, beefier, built up, engineered better, tighter tolerances. Everything on a diesel is going to be more expensive. And that's why if you blew a Duramax up and you need a Duramax, it's going to be 30 grand for the engine alone. Makes sense? So that's just mega bucks. But technically though, the diesel fuel does have more energy in it as measured by British thermal units. Just is what it is. Coal, as you can see, is not great. 8,000 to 12,700, depending on what type of coal it is and where it came from. But this is what we used to do. Makes sense? So if you have a car, nobody's shoveling coal into your engine. However, if you have a power plant, you can get coal a lot cheaper. They can say how many BTUs are in the coal power in the coal, and then you can, you know, make electricity out of a coal power plant. You know, that's still what we're doing, right? It sounds like it's 100 years ago, but they're doing that like right now, like today, right now at this very moment. There's some machine is putting coal into the power plant and making electricity. And my Tesla's in the parking lot charging. Shh. I'm gonna get a green sticker, be like green, like Mother Earth sticker, but I'm literally charging it. Actually, during the day, what time is it? You know what? Solar's probably cranking right now, but when the sun starts to go down, the coal picks up, partner. The sun goes down, the coal comes up. So right now it's charging on solar, so I could put the green sticker on there, but like in another few hours, I should probably take that bumper sticker off of there. At least most of you guys are burning the gas, and I'm gonna be burning essentially coal through electricity. Just calling it how it is. I don't feel bad though. All right, so like we were kind of getting, you know, I think we're probably pretty solid on that. So let me skip a couple things. Let's talk about force, work, and power. All right, let's see. Who's it going to be? Oh, this is definitely going to be Rudy. Rudy right here. How much is it going to take to pick this up? Well, 150 pounds. For you to move that, you have to generate 150 pounds of force. Would we agree? So that's just force. The effort to produce a push or pull action. So you're going to try, you need to generate 150 pounds to move this, right? But the question is, how far are you going to move it? Ooh. Well, like in this case, 150 pounds of force is all you need. But if you need to move this weight 4 feet to get it right here, that's no longer force. Make sense? Force doesn't have a distance associated with it. Cool. That's a measure really of work, right? So it's kind of interesting. If you look at the two, work is when a force causes movement. Work is done. So look at it like this. That 150 pounds, I'm making, that's about 150 pounds right there. Maybe 200. Are we kidding? All right. So did I do any work? No, I didn't move anything, right? So I generated a force, but I did no work. So a force is cool, but like it doesn't really accomplish anything. Generally, that's part of the reason that we don't worry too much about how much force an engine makes, because it's not necessarily usable. We need to add a distance in there, right? So then if you look at work, when force causes movement, work is done. So technically, did I just do work? Yeah, I didn't generate a lot of force, but I moved something. I performed some work. Make sense? So sometimes when people are moping and, oh, I worked really hard, and I look and I'm like, yeah, but you didn't get anything done. So actually, it just means you tried hard, but you didn't do any work. You just, you know what I'm saying? Like, what did you, work is physically moving something, okay? And then if you look, it's equal to distance moved times force applied. So if you did 150, let's do it 150 feet, and you did it 1 feet, 150 on that barbell, but you picked it up 1 foot, it'd be like equal to distance times force, 1 foot times 150 pounds. And that would be an amount of work. Make sense? Kind of? Pretty interesting. And that's why we measure it in foot pounds. So you moved 150 pounds 1 foot. You could also make it 100 pounds 1 foot, which would be 100 foot-pounds. Right? So that's just to understand the units of measurement. Now we won't go crazy into the math, but everybody struggles with what's the difference between torque and horsepower, right? You've heard this conversation so many times, right? Torque is really a measurement of work, but so it's foot-pounds. We agree? Foot-pounds, pound-feet, if you will. Pound-feet of torque. Great. How fast is that going to move a 4,000-pound car down a 1/4 mile track? 1/4 mile. 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 1/ You know why the math doesn't work? Because I just introduced time, right? Work, foot-pounds, has no time. So if you want to know how quickly it's going to get done, you need to actually not calculate work, you need to calculate power. So that's the rate or the speed at which work is performed, right? So if I moved my phone from here to here, I did work, but it was not very fast. So I'd have to do it like this. Like, how long is it going to take you to, I don't know, let's just say move 4,000 pounds a quarter of a mile. If you have a lot of force, you know what you could do? You could pick up the 4,000 pounds and you could carry it a quarter mile and be like, boom, there it is. I'm done. And I did it in 10 seconds. There's your 10-second car. Make sense? Or you could be like, ooh, well, I can't carry 4,000 pounds, but I can carry 100. And then you're going to have to do that trip 40 times. And you'd be like, yeah, I moved your 4,000 pounds a quarter of a mile down the track, but it took me all day. That's not a whole lot of power, right? You don't have as much power. So it's explained in 100 different ways, but if you really think about it, torque is just a measurement of how much force an engine can make or how much force a torque wrench can apply, but it doesn't have anything to do with how fast it can do it or how much time it will take to do the work you're asking it to do. Cool? So if you talked about, I don't know, you guys tell me, what type of horsepower do you want? What do you want to scoot your butt around town? 500. Why is 500 horsepower better than 250 then? It's just going to feel cooler. True. But the reason it's going to feel cooler is it's going to move you along faster. Make sense? I mean, literally, if you think about it, it's simply because it's going to move your butt in your seat, your butt being the butt dyno, faster. So you'd be like, oh yeah, this car's definitely got more power. This car's definitely got more power. I can tell because of my butt dyno. You felt it move your car faster, right? Whereas, how did it do it faster? Well, it probably also is making more torque, but not necessarily. I'll give you an example. Let's say a street bike, let's say like a 600cc crotch rocket, if you will. You know, those, they can make actually pretty big power, to be quite honest with you. Let's say it makes 100 horsepower. A lot of them are making more than that now. 130 out of a 600 is not unheard of. But if it's 100 horsepower out of a 600cc, and then you actually look at the torque, it's probably like 60 foot-pounds. And then you're like, what? It's only got 60 foot-pounds. How does it have 100 horsepower? Then you might get, let's say, like a Yamaha R6. Those rev to 18,000 RPMs. That might be like 130 horsepower and still have 60 foot-pounds. So you're like, wait a minute. If you got this Harley Davidson engine that makes 60 foot-pounds and you got this Yamaha engine that makes 60 foot-pounds, they make the same amount of crankshaft torque. How come the Yamaha can have 130 horsepower and the Harley might only have 100 horsepower? They make the same torque. The weight's a good point, but not, the weight has nothing to do with the power the engine makes. It has to do with RPM. So if you think about it, the higher the RPM, it's equivalent to work if you think about it, right? The revolutions per what? So there's time right there. Foot-pounds has no time, horsepower has time. When you have, let's say, that R6 having 130 horsepower, that is definitely going to get down the track faster because it has a lot more horsepower. But to do it, it's probably going to be up near red line, right? That's why when you're racing, you want your power in the red line range. You want it right where your most horsepower is made because that's able to do the most amount of work, the highest amount of work. Technically, though, when your crankshaft makes the most force, it might actually be lower than your red line. It might be lower than where you make your most horsepower. They tend to be a little bit different. When it's making the most torque is one thing, but when it's moving really fast and performing a lot of work, because every single time it has a power stroke, that's work, that's work, that's work. They're a little bit different, right? Now, if you were to take that 600cc, right, it's got 130 horsepower with 60 pound-feet of torque and put it in a tractor trailer, how well you think this is going to go. I don't know if it'll even get it moving. Make sense? But you're like, hey, the tractor trailer engines, you know, they only a lot of times make 500 horsepower, sometimes 4. Do you know that? Big, heavy tractor trailer diesels don't make a ton of power. You know what they make? Ton of torque, right? So they can generate a lot of force on the crankshaft, but their RPM, their red limit, their red line may be like 3,500, 4,000 RPM. Like my last tractor was like, I think 4,000 RPM or maybe 3,500. So that's it. Yeah, the diesel made a lot of torque and it could do a lot of work, you know, lifting the bucket or towing a trailer, whatever, but moving it at a high rate of speed, not necessarily so much. It's just not really the concern for those. So you may have a really high horsepower bike that doesn't generate a lot of torque. It's not going to be able to get the things moving. But when it's a tractor, you don't really need it for the quarter mile. You know, you really need it to lift a bucket full of rocks or move a heavy trailer, right? So horsepower and torque, you need torque to make horsepower, right? But torque doesn't consider the rate at which the work is performed. Okay, cool? Kind of crazy, huh? All right, so when we do the power, it's the rate or speed. The more power that can be produced, the more work that can be performed in a given amount of time, measured in foot-pounds per second, foot-pounds per minute, watts or kilowatt, or like in our case, we'll probably use horsepowers. Do you know what horsepower is? They figured out how much work, how much power a horse had, how much work a horse could do in a certain amount of time, right? So you take a horse and be like, hey, how many buckets of water can you haul out of this well in 60 seconds? And the horse is like, 10 buckets. Cool. That horse did 10 buckets of water in 60 seconds. Nice. That's 1 horsepower. Then you got this Briggs and Stratton, and you're like, and it's 5 horsepower. How many buckets of water should that be able to do in 1 minute? The horse did 10 with 1 horsepower. How many buckets of water should the Briggs and Stratton do? It's a 5 horse, and the horse did 10. 50, yeah? So if the horse, it should be 5 times the horse because it's a 5 horsepower. That makes sense? 1 HP, because it was a horse, did 10 buckets. A 5 horsepower Briggs should do 5 times that amount, which is 50 buckets. And by the way, the well is 100 feet deep, right? So 100 feet deep, that's not how you write 100, in 60 seconds. All right, so you have everything you have there. It moved a certain amount of weight, a certain amount of distance, and a certain amount of time. That's why we use power, horsepower. Make sense? No, you hate it. Fine, we're moving on. We're definitely moving on. All right, so then here's your horsepower, for example. Here's Rudy. Now we know that Rudy's moving in fast speed. So he lifted 150 foot-pounds, 4 feet. Congratulations. But he did it in 2 seconds. Now that's actually power. That's horsepower. That's how much work you're doing. If it took you all day to lift 150 pounds, 4 feet, you might have made a lot of torque, but you didn't do a lot of work. Make sense? Like that. Cool. All right, so breaking it down, torque, twisting force, movement doesn't have to occur, okay? It's applied before or during movement. So that's where it gets a little bit weird. If you guys go to tighten a lug nut, right? And your torque wrench clicks at 100, you did apply force. You just didn't necessarily have movement. It's still kind of like torque. It's just, you didn't really do any work. Make sense? So there's your torque. Rotational force applied to the crankshaft of an engine is called torque. Yes, we know that. Unit of measurement, foot-pounds. Cool. Now the formula for horsepower, this is where it gets weird. Horsepower equals RPMs times torque. Make sense? Then it's divided by 5,252. I actually don't totally know who came up with that number, but that's how we convert it into what a horse could do. Okay, so let's break it down. If you had that 60 foot-pound Harley, I don't want to pick on Harley. I'm going to soften a little bit. That 60 foot-pound tractor, no brand name, no nothing. 60 foot-pound tractor with a maximum 60 foot-pound tractor with a maximum RPM of 3,500. You could even do the math. Then you had a 60 foot-pound crotch rocket with a maximum RPM of 18,000. Which one is going to make more horsepower? All right, think about what I just said. Horsepower is RPMs times torque divided by the horsepower number. So let's just focus on RPM times torque. If you had 60 horsepower in the tractor and it redlined at 3,500, and then you had 60 foot-pounds on the crotch rocket, but it redlined at 18,000, which one is going to have more horsepower? For sure. And it's going to do work a lot faster, right? And so that's more like the lesson right there is, yes, they both take torque to do work, right? But then you look at revolutions per minute. The crotch rocket engine is turning really fast, so it can pull up a lot more buckets a lot faster. Make sense? If they can both lift the bucket 100 feet, no problem. But one of them's at 3,500 RPMs. And the other one's at 18,000 RPMs. Which one's going to do more buckets? Thank you, the crotch rocket, right? So that's more just the visual. Cool. But that is the formula, so you know. So a lot of times horsepower is calculated. You can, of course, measure it on a dyno. A lot of times the dynos have their own electromagnetic way to load the engine, or sometimes use water or whatever, and we measure how much work it does in a certain amount of time. That's how we measure the horsepower. Cool. Or you can measure it in kilowatts, which is more normal for electric motors. Makes sense? In fact, actually, sometimes they do measure electric motors in horsepower. They'll be like, oh, that's a 3 horsepower electric motor. That's a big electric motor. But most of the time, they're going to measure it in kilowatts. Cool. All right, so overall, I think you get it. Now, when we start talking about the load factor or the power range, this comes into how the engine is designed, how it's made to work. If you want an engine that can run all day, every day, you know, at 50% of its red line and just do work for 8 hours, honestly, a typical gasoline engine is not going to be real happy with that. They'd usually go over to a diesel and they'd build a diesel to be able to do that. Cool. So if you went on a construction site, you see somebody moving dirt all day, right? They work 8 hours a day. That's their whole shift. They just move dirt all day. They're going to design an engine to be able to do that all day long, every single day. Make sense? You think that's what our cars are designed to do? Your average car, you think somebody jumps in there and just moves dirt with their car? What do you think they're doing with their car? They move their butt from their house, from their couch to their job a half an hour away. And then it sits in the parking lot. And then they get in, they do it again. And then guess what they're going to do tomorrow? They do it again, right? So our cars are designed mostly for that. If you wanted something that was going to move dirt for 8 hours a day, plus sometimes these things are multiple shifts. Like, so locomotives, for example, when I worked on those, a locomotive would get started, sit there and idle. We'd do the checks. It would run from here to Texas. It would get there sometime 24 to 36 hours from now. They'd leave it running. They'd unhook some things. It'd still be running. It's now been 48 hours. And then they'd literally leave it running. You could check the oil while it's running, and they'd turn around, they'd send it back. It may be running for 48 hours, 3, 4, 5 days sometimes. Those were made to run for days and days and days and days. They're just designed way different. That's what they're made to do. Kind of make sense? So all these factors come into how the engine's made. It's not just as simple as like they put pistons in, they call it a day. Make sense? Cool. So if you have an engine that's supposed to be super powerful, like a GR Corolla, it's not made to be at 7,500 RPMs 8 hours a day. I'm not saying you can't do it sometimes. It's made to do it sometimes, but it should not be ram, bim, 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 bim for the next 4 days straight. Make sense? It's not made for that. Will it take it? I don't know. Maybe the Honda will take it. I'm not sure. Honda. Okay. But that's like I'm going to have a guess that the engineers probably didn't design it for that. Makes sense? So this all is official. You know, that's how they're designed to be one way or another. They're designed for a specific purpose. Let's just say that. Lawnmower, for example. You buy a lawnmower for yourself at Home Depot or Lowe's. That lawnmower is designed to run for half an hour to an hour and then be shut off till next week. If you want to start a landscaping business and you want to push it and mow this lawn and then go to the next one, or if you want to do a baseball field and have it running for 4 hours at a time, that's a different, like you're into commercial. Those are designed different. They cost a lot more money. A lot of times they have bigger cooling systems and bigger oil capacities and bigger stuff. And the one that's for sale at Lowe's right now is like Hecha in China for sure. Make sense? Like not going to really but it'll be fine for homeowner use. Make sense? In a way, yeah, it's what it's designed for. The longer and harder you run something, heat just builds up, and the more heat builds up, you start to have some parts get hotter than other parts, and now you have things that are not shaped exactly how they were supposed to be shaped. So you got to manage all that heat. It's much harder to do. Diesels, though, are better at that. If you want something that's going to idle for a long time, be honest with you, like a lot of the police cars would do better as diesels. Because, you know, they're just leaving them running a lot. They got to be hot, ready to do a high-speed chase. Diesels would probably be better for them, in my opinion. Go ahead. Yeah, I mean, and that's what they're made for. But, you know, typically when you look at a newer modern car, big cooling fan, you know, it's electric cooling fan. So we're not relying on higher RPM. You got a lot of various sensors that are looking at the parts. Oh yeah, they're fine. Any modern car is made for road trips too. It's just not really made for like stop and go traffic, like a taxi cab. A taxi cab is going to be hard use for an engine. It's going to be pretty hard use. But for a road trip, it could easily do those. However, I wouldn't say they're designed to do like a road trip and then leave it idling and then drive all the way back and be 16 plus hours a day every day. Like it's probably not going to hold up all that well. But at the highway speeds, it's a little easier on them. The stop and go is what's tough, for sure. All right, pretty good. So then we get into like, remember horsepower, twisting force. Torque, twisting force. Horsepower is the rate. So there's your dyno. Okay, then when we get into the factors that affect an engine's torque output, has to do with volumetric efficiency. So that's a big term you guys are going to see. The volumetric efficiency, picture it like this. When we talked about that intake stroke, the intake valve opens, the piston comes down, it pulls the air in, but the thing is, the valve's got to close kind of quick because the compression stroke is coming up, right? So you get a certain amount of time. Intake valve opens, it pulls it down, intake valve has to close. Was that enough time to thoroughly fill the cylinder? If you could completely fill the cylinder with air, that would be 100% volumetric efficiency. Try doing that at 8,000 RPMs. At 8,000 RPMs, that valve is open for such a short period of time, you're probably not getting all the air molecules all down into that cylinder to 100%. Does that make sense? So your torque is actually going to fall off, right? You're going to make your most torque when you're having a really good volumetric efficiency. When you get close to red line, to high RPM, your torque number a lot of times will fall off, even though your horsepower number might keep going up because you're still doing more RPM. You're still doing more revolutions per minute. Kind of interesting. Cool. And that's kind of what it's saying. Then the other thing is you look at internal friction, the limits of the intake and exhaust. All these are things that are going to affect that. Naturally aspirated engine torque typically is going to peak a little bit lower than horsepower. And you can see it's going to start to drop off. So like right here, if you guys look, your torque started to fall off around like 3,500. Your horsepower kept building until 4 a little bit more. Makes sense? because right here, you're no longer totally filling those cylinders with air because your valves are closing so fast. Makes sense? It's like you open the valve and as much air came in as possible, but then you had to close it kind of soon because you're at 3,500 or 4,000 RPM. Well, maybe there's a little couple pockets that didn't get totally full with air. You guys kind of understand volumetric efficiency? So your volumetric efficiency could be really good down here, but by the time you're at 4,500, your volumetric efficiency is dropping off. And you can see even by then your horsepower is dropping off too. How do you think you can improve that? Well, like for one thing, you know, it's kind of hard to have all the air flow in when there's a little bit of exhaust gases left over in the cylinder, right? So this is a good way to get those exhaust gases flowing a little faster, right? Or let's just say, do you guys remember what actually causes the pistons to open and close? Kind of, right? So here we got a cam lobe right here. What if you were to open up the valve further and that allowed a bigger opening? Do you think more air could come in? Oh yeah, so maybe you know what we should do? We should put a bigger, fatter cam lobe on there. A bigger high lift cam lobe, a little performance, a little like something like that, huh? Like that, like a little chop, right? So sometimes changing the camshaft can improve your volumetric efficiency. It can, but there's all these little factors. Then you go with a big cam and your volumetric efficiency is good at high RPMs, but at low RPMs, there's such a long duration. Now your idle's funky and your brake pedal's hard because your vacuum booster. And so the manufacturer is constantly trying to fine tune these. And then you'll get into varying the timing of the camshaft, or even this for you, Honda man, we'll even do variable valve VTEC, where we've got a low speed cam lobe. And then, you know, at how many RPMs does your VTEC kick in? My motorcycle kicks in 7,600. All right, so 3,500, 6,000 for S2000, 7,600, I think, for my VFR. All of a sudden, this VTEC solenoid will be like, hey, get off that little cam, get on this big cam. All of a sudden, the volumetric efficiency comes way up, and there's a burn, you know what I mean? When VTEC cracks, is that what they still call it? Burn, VTEC kicks or whatever. Yeah, that's why. So if we added VTEC to here, you might actually see an increase in the volumetric efficiency, so your torque will go up and your power will carry up even higher, right? So that was Honda's way to get more horsepower and higher volumetric efficiency. And then Toyota's going to use VVTi, and everybody's using, BMW's use Vanos, you know, they got to be special. You could say Nissan's going to use VVTEL or something. They all have different names, different technologies. Go ahead, Rotseni. Generally, horsepower and oil are unrelated. So despite the forums, everybody wants to use the one with the shiniest bottle and stuff. You're not gaining horsepower. If you're honestly gaining horsepower because you changed your oil to a different one, there was something severely wrong with the first oil if it was adding that much friction. So oil should help the lubrication, help the heat, you know, help minimize any wear, but free up horsepower? Nah, I don't think so. Unless it was sludge going through there, which is scary, and I have seen it. All right. Now let's break down a little bit of those other terms. TDC and BDC. Everybody got TDC? Top dead center. That's as high as it goes. Top dead center is the highest point of that piston. So a lot of times when you go to time stuff, you might need to set top dead center. How would you find top dead center? Sometimes there's marks on the timing components. For example, I've got a little sprocket here. You're good right there. There's a little dot on that. You guys can see that dot. How about the light, huh? How about the light? Look at that little dot. Ooh, overkill. Oh yeah, right there. I got it on bottom. How about if I went to top? You could see it's right about at the top now. So there's timing marks, yes. But if we're talking about the cylinder, you know what you could do up here? Take out the spark plug, set a little extension down in there, turn over by hand, and the spark and the extension is going to go. Wait, back it up. Too far back, right? So you can just fine tune it where the extension's at its highest. They also have a compression whistle. You take the spark plug out, you put this little hose on with the whistle on, and you'll turn it and it'll go. and you can fine tune it literally by sound. Whatever, you got to find it how you got to find it. It's okay. Now I'm going to say this loosely though. For 99.999% of engines, if you go too far, just back it up. No big deal. Shouldn't be an issue. Now there's like very, very rare instance. In fact, I'm going to get the attention over to this engine for a second here. Let's do that camera. Let's do that light. You guys can see this engine has a timing belt. Can you kind of see that? All right. So this timing belt is actually slightly loose. There's once in a great while, if the timing belt's really worn and the tensioner's really sloppy, you'll go to back it up and sometimes it can jump a tooth. All right. So this is something that it's actually happened to me once, but I was working on all kinds of stuff. Most people will never experience it. However, when it happens to you once, you're like, don't ever turn it backwards. Don't do that. It'll jump it. Like I turn them backwards all the time. This one I had that was doing that. It actually had a problem with the tensioner. The tensioner was flat and it was enough to keep it kind of tight and forward. But when you went to back it up, all of a sudden one of these teeth jumped the cam, right? And I ended up a tooth off because I turned it backwards. All right, we're good. But normally that's not going to be what we see. That'd be very exceptional. Make sense? All right, and then what's BDC then? All right, so from bottom dead center to top dead center, there's a measurement right there. And you know what it is? It's called your stroke. So if I were to go piston, bottom dead center, make a mark, and then go all the way to top dead center, make a mark, that distance right there is called your stroke, okay? If it's a 3.5 inches, that would be like a small block Chevy. That'd be like a small block Chevy, like that. All right, makes sense? You know that one, huh? You seen that guy? That one was small block Chevy. Right, so that'd be, or sometimes what they'll do like, I'm gonna take my small block Chevy and I'm gonna do a stroker kit. I'm gonna go from a 350 to a 383, and they'll take the stroke from a 3.5 to like a 4-inch stroke. And how they do that is actually they have a bigger offset on the crankshaft journal, and then they use a shorter rod, right? So you can vary the stroke. If you think about this, the further your stroke goes down, it's still got to go back up to TDC, right? It's got to go right up to the edge of the head. But if you pull this down further, why is that a benefit? Air is good. I mean, overall, let's just go with displacement. How about that? Because in a moment, when we talk about TDC to BDC, that big section right here, this is going to end up becoming your displacement. This little combustion to this big area, that's your compression ratio, but your actual displacement is going to be TDC to BDC, but not in just inches. That's the stroke. It's going to be the stroke times pi r squared, is how you're going to figure out like the surface area of a circle, pi r squared. So it's going to be this whole area. The other way you could do it is you could basically put some water in this. You wouldn't do this in the field, right? But as a visual, you would fill this with water and then pump it up to TDC and see how much water came out. And if it came out with, I don't know, 200 cc's of what, that's a 200 cc displacement. That'd be per one cylinder. And if you have 4 cylinders, it'd be 200, 200, 202. Oh, you have 800 cc 4-cylinder. So that's a 0.8 liter. Kind of make sense? Yes, exactly. Now, I don't know that they use water. They probably use CAD or CAM or whatever, some computer program. But like for a visual for us technicians, yeah, just picture the water. Yeah, so like in a Honda 2-liter, you'd have basically a half a liter per cylinder. So if you were to go TDC to BDC, that's going to be a half a liter. There's 4 cylinders. Half, 2 liter, 2.0 Honda. Make sense? 2 point what? That's what I thought. Right? Or if you had a small block Chevy, that would be like a 350 cc's, 350 cubic inches, not cc's. Cubic centimeters is different. Cubic inches. All of your cylinders combined would come to 350 cubic inches. There'd be 350 cubic inches of water, which is really more air, but so you know, that's what displacement actually is. Yeah. It does, but it shouldn't. So I'll bite. If we had an issue with these rings right here, or a score in the cylinder, or some major issue, oil could be left on the cylinder wall, which will then end up in the combustion, and it'll it'll burn, it'll smoke. It'll be blue smoke. So kind of, yeah. And we'll get a lot into this right here. For now, it's a little more basic. But when we get into the bottom end, yeah, we got to be very concerned about worn rings, worn pistons, worn cylinders, and that type of stuff. Leading to oil consumption, because, well, a couple issues. When it consumes oil, that means your oil level's dropping. All this internal combustion engine stuff is pretty amazing, but if you don't have oil in there, it's going to blow the cookies out the bottom, blow up. Like you guys know, my last bike, I blew that thing up on the freeway. I locked it up. And actually it had oil in it though, so I guess it's kind of bad. I beat that bike so bad. 6,000 RPMs for 2.5 hours a day. It did well. It did for like 6 years. But if you had a brand new engine and you had low oil in the crankcase and those bearings got dry and they got friction, little friction weld, blow it up. So when we say blown up, it's usually friction down here in the crankcase, locking this rod up, spinning a bearing. I got some rod bearings and stuff I'm going to show you. So oil consumption, similar to this, but it has more to do with bottom end, which I promise we will definitely cover. All right, cool. So you guys are good with TDC and BDC? All right, very nice. All right, how about what if we had two strokes? I think I'll just give you like a brief preview of a two-stroke. Remember how we talked about the 4-stroke cycle? Intake, then what? Compression, then what? Power. Combustion or power, interchangeable, good. And then exhaust. A two-stroke's kind of weird. I'll give you just a few words on it, but then mostly what I want you to do is watch the video I have in the discussion. A two-stroke is going to be like TDC. It's going to come down, and it's got ports that are going to be exposed, and it's going to pull intake air and fuel into a port. So it doesn't have valves. It's got actually a cutout. It's going to pull some in. It's going to go down to complete its intake stroke. And when it comes up, it's going to be kind of like exhausting the other stuff that was still in there, right? So it's kind of weird. It pulled in some new air and fuel, pulled it in, but as it goes up, it also kind of pushes out the little bit of air and fuel from the last stroke that's left over. Then it comes up and it's actually going to compress, then spark, which is going to ignite, combust, and a power stroke's going to come down. But then when it gets halfway, the power stroke's kind of done. And then remember, it starts to suck air and fuel in the port. So it's almost like, if you think about it, it did it like this. It was kind of like power intake, exhaust compression. There's only two strokes, but they're sort of combined because it has holes in the cylinder that we call ports, and they put them in certain spots. The two strokes kind of weird. I've tried in a million ways to explain that. And honestly, the only way is if you watch some animations and then you're like, oh, okay, I kind of get it. And then even if you don't get it that well, that's okay, because we're not doing much with that. But somebody at some point in your life is going to ask you to explain a two-stroke. I want you to at least kind of understand it. Good news for you, there's no two-stroke stuff on the ASE. As far as I recall, there's no rotary stuff on the ASE either. All right. Pretty good. Now, when we get more in detail, if it's strokes, we're going to call it reciprocating. So if it's a 4-stroke, intake, compression, power, exhaust. If it's a 2-stroke, it's kind of like I said, like power intake, exhaust, compression. Cool. We may have inlines. You guys know about those? Inline 4. Don't even need to move it. Inline 4 right there. If you got an engine that's on a V like this, oh, you do? Might need to move it a little. Inline 4 right here. Whoa, nice, man, because we got 4 cylinders right in a line. What if you've got an engine like this? All right, good. So you know enough where we can proceed. We're going to see a little bit more. Now let's take a look at the primary components. So this is where we get into like the bolt-on parts of the engine. So if you look at this, we have got, let's start with the intake because that's where the air starts. Then let's bring it over here. We're going to get a good look at this. We're going to leave it over here. We're going to be back and forth on this a bit. All right, if you guys look on this engine right here, you see this metal intake. I'll tell you what I'll actually do. Let's take a look at this. Intake, exhaust. We'll do intake, head, exhaust, block. All right. So now I'll put it up so you guys can all see it pretty well. This will be a cool little trick that I haven't done yet, but today's the day. That should have been on. You guys are on the Zoom. Is that off? That you were seeing the main screen before, right? Abner, what you got? Okay, but it wasn't like that before. It was. Good. Don't click it. Just leave it normal so I can see what it's showing. So right now we should be not doing the screen share. Okay, that's what you guys should all be seeing. Let me pull it over to here. Okay. You guys can see this big old intake right here. What do you want to call that part? So this is the whole intake manifold. Some other parts would be right here. You can see this. Burp, 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 burp. Yeah, so there's our throttle body. This is all part of the induction system. So if you guys can see, air is going to come in here through the throttle body. Burp, burp, burp. And then it's going to go from, and you know where it comes from before that, right? The air box and the air filter, which is going to have the mass airflow. It's going to go into this manifold, and can you tell it's going to split it 4 different directions? All right, so if it splits it 4 ways, that's why it's a manifold. Comes in as 1, splits it to 4. Then if you can kind of see, the intake is bolted onto the head, and that's why I get to spin this all around. You see that the intake ports are going to go to the head. Then you can even see a little bit in that cylinder. All right, so right there, anything from my hand up is the head. Anything from my hand down, you can see this is the head gasket in here. Well, you could kind of see it. Down is the block. We call that the bottom end. We call this the top end. Cool. So the air is going to come in. It's going to go into the cylinder head. So there's a valve in there, which you might maybe kind of be able to see somewhat. But the good news is for you, I brought one anyway. All right, so here's an example of a valve. It's going to go up to this intake valve, and it's going to wait. Now, what's going to make this intake valve open? All right, look over here. Depends on the design, but let's just say this valve has a bucket on it. That's a bucket. And then that bucket is going to be driven by the cam, okay? Makes sense? So right now, that's closed. As I rotate this cam, we'll notice there's a point. Can you guys see the point? As the point rotates to it, what's it going to do? Push it down, and then it's going to bring it back up, right? So there's the action of the valve. Now that was a bucket design. Those are basic. We'll also a lot of times use a lifter. The cool thing about a lifter is the roller will roll on the cam. Now this one's from a small block Chevy. So that's a cam in block. So the cam is in the block. The lifter follows the cam. It's going to push up on a push rod, which is going to push down on a rocker, and that's going to open and close the valve, right? But if you just understand this is going to roll on the cam. I'll fib to you and I'll say it goes this way, but it doesn't because it's not from an overhead cam. But this would roll on the cam, and then it would push the valve down. But you know what the positive of this is? This is a hydraulic lifter, a hydraulic lash adjuster. You don't have to adjust it. It gets pumped up with oil and it keeps it tight, but it makes up for a little bit of wear. Don't even move. The thing is, if we have the bucket style, this bucket right here. This is good. It's more simple, but as the valve wears into the head, we need to shim this. You guys ever heard of adjusting the valves or shimming the valves? That's where it gets a little tricky. So like this one, this is number 43. You'd actually have to take this bucket out and put in a 42 or a 41, depending on your measurement, right? And so these require a lot more maintenance, right? And now that's the intake. And then we got into the cylinder head just a bit. From this side, you can see it better. All right, what can you see right there? The air is going to come in through that intake valve, go in the combustion chamber, which I can actually turn this, get you a better view. Ooh, that's hard to turn though. All right, you can see in the combustion chamber right there, you can see these two exhaust valves. So the air will go in the combustion chamber on the intake stroke when the cam pushes the intake valves open. And then it's going to do compression, which both valves will be closed. And then when both valves are closed, the piston comes up to TDC. And what's actually going to happen at that point? Do you remember? Spark, right? So if I look right here, see this? Here's the spark plug wire. The spark plug's down in the hole, and the spark plug actually comes through. It's just a little out of sight, right? So the spark plug's into the actual combustion chamber. Yeah, I don't think anybody can quite yet, but it's okay. We'll see pictures too. So when the spark ignites the air and fuel, it's going to push the piston down, right? So that piston's going to start to go down. I have turned this engine, but it's pretty hard to turn. I may be able to. Yeah, there we go. There we go. Oh, all right. Put a hand on that alternator there, Shani. All right, here we go. Come on, get that lighting right. I think you got to get the light closer. You got to get above that. Yeah. With the light. You can it's so hard to turn, but you guys can see a little bit of the movement. The piston's coming back up now. Oof. All right, let me try. What if I'm in? Yeah, click, click. Actually, maybe no light. I've also got it turned too much now. How about in there? David, you're hired. You might be able to see something. I'll try to turn it. Oof. It's tough to turn though. Yeah.
Oh, you can see it. Yeah, you can see it.
All right, here we go. Here we go. You can kind of see it. There. So you saw us get pretty close right there. All right. It's too exhausting to do, so I'm going to roll it up a little. So you guys saw when we got to TDC, that's when we'd fire the spark plug, right? That would give us the compression stroke. When it gets to BDC, what needs to happen? We need to exhaust it. So you know what we need to do? This exhaust camshaft needs to open that exhaust valve, right? So we got the exhaust valve closed. The exhaust camshaft lobe should be timed in such a way that it'll start the push down of the exhaust valve at the right moment. And then if I were to rotate again, which is pretty hard to do, you'd actually see the piston coming up and the exhaust valve is open. And that exhaust is going to port into the exhaust manifold and out. And ultimately, where's this going to go? Out to the tailpipe, yeah. Yeah. What cat? Oh, straight pipe mod. Okay, no meow. All right, cool. And then I think you guys can take a look at the timing components real quick here. Because we talked a lot about, here's your crankshaft. Cool, so this is what I was turning. You could see it's pretty hard to turn right there. The crankshaft, thank you. The crankshaft will turn, but not only that, the crankshaft will turn the belt, and the belt will turn the water pump, and this is the tensioner, and ultimately it'll turn this camshaft, and this camshaft goes to another camshaft. So this has dual cams, but only has one sprocket. So this we'll say is the cam that drives both cams. So as I turn this, you'll notice it's turning the sprockets, and everything has to be in time. Now, if I were to make this, if I were to be If I were to make a boy band and I wanted to have it be about being in time, what would I call myself? Oh, in sync. Everything needs to be in sync. When it's top dead center and we start coming down, I need to open the intake valve. The camshaft needs to do that. So therefore, this camshaft needs to be timed to the crankshaft through the timing belt. And then I get to bottom dead center, and then both valves should be closed because it's in sync. I don't really know the songs. I can't. However, but you get what I'm saying, right? In sync, they need to be in time. Cool. And then if you think about it, it's kind of crazy, but as I'm turning this crankshaft, the camshaft only turns half the speed. Makes sense? So if the crankshaft turns a half an RPM, and I'll even hold the piston and a valve right here, this piston, this valve, if the crankshaft turns a half an RPM, a 180, the piston goes from TDC to BDC. Cool? And if it was on intake, I'll open the intake and I'll go to BDC. Then I'll close the intake. Then I'll compress it, fire the spark plug, and then on the way back up, I'll open the exhaust valve. Cool, but think about that. We had to go 4 strokes. That's a 180, a 360, a 720, a what? A 180, a 360, a 720. Yeah, what's before that? 540. Yeah, sorry about that. 180. See, I haven't snowboarded a long time, huh? 180, 360, 540, 720, right? So 720 is 2 full rotations. 360 times 2 is 720. The crankshaft has to turn 2 times to do the 4 strokes. Make sense? How many times did the intake valve open? Only 1 time. So we need this to turn twice and the cam to turn once, so it'll open the intake valve once, and the exhaust cam turns once, so it opens the exhaust valve once. Make sense? So if you had a 10 sprocket crankshaft timing belt sprocket, you'd have to have a 20 teeth timing belt sprocket for the cam to make it turn at half the speed. Does that make sense? Kind of weird, huh? A little trippy if you think about it. So the crankshaft turns twice as fast as the camshaft, right? And then with all that, I'll even whip it around here, and you can see just a bit of the crankshaft. Cool. Pretty nice to see. You can see the crankshaft. And down here is what's considered the crankcase. That's more like the oil pan. The crank case is in here. The oil is going to be down here, but right here is going to be like airspace. And if you overfill the oil will get into the crankshaft and get foamed up. Okay, that's why we can't overfill the oil. But if you underfill it, we got a big problem. So like if you pull the dipstick and you put the dipstick in, there's nothing on the dipstick, you run a major problem. This oil pump right here, which is from a small block jibby, this dips down into the pan, but what if your oil's so low it's sucking up air? You're not going to put pressurized oil all through the engine, and you're going to have a lot of friction. You're going to burn some stuff up. It's going to get messed up fast, right? So this is your oil pump pickup. Your oil pump is driven by something on the engine, maybe driven by the crankshaft directly, sometimes driven by the camshaft, but the oil pump is not belt driven. Now there's one exception on on a couple of the new diesels, they're making a timing belt driven oil pump, which is freaking nuts, and stupid. You can tell them I said so, but generally this is driven by the engine. So you don't get oil pressure till you start the car. Cool. Then once it's running, you can kind of see some of these other parts, and I think probably we're decent on this. You can see a little bit of the cooling system on here. Like here's your thermostat housing right up here. This one's old school. It actually has a distributor, so that's definitely pretty dated. I also have a eccentric that I was hiding in there that I now stuck. All right, so I think we're probably okay on there. Let's, we're going to switch it back up. All right, definitely. Going to go to screen share, screen 2, share. All right, this is what you guys should be seeing on the Zoom. Hopefully I had it on that. Otherwise, I kind of messed that video up if I didn't. See if I can fix it. Okay, so you guys saw the intake, you saw the head, you saw the exhaust. and you saw really the block, and we split right here where the head gasket lives. This is top end and this is bottom end. Then you got the oil pan. We didn't really count that. And you got the head cover, the rocker cover, or the valve cover, interchangeable names. We didn't count that. You explain that short block? Yes, but I have it later in the presentation. But absolutely. And we'll keep an eye on the time. So I think we got a little bit, I think we can do a little bit more. You guys heard it and you want to keep rolling? All right, we'll go at least a little more before we stop. All right, so here's your head in more detail. If you look at a cutaway side view of the head, we've got the intake port. So what do you think port means? Yeah, it's like a passage, a channel, a hole. So when you hear it's ported and polished or something, that just means somebody came through and like fine-tuned the shape of that port. Port's the passage. Now right here we got an injector. So if you don't know anything about this, I'm going to help you. If the injector's in the intake port, what design fuel injection would you suspect this could be? Port fuel injection, because the injector is in the intake port. That's port fuel injection. You guys have heard of direct injection? Direct fuel injection? Where's that in? Well, all the manufacturers doing it, but like where this spark plug tube goes through and the spark plug's in there, you'll actually have an injector here, or in Toyota's case, they bring an injector kind of like down on the bottom. That fuel rail's like way down here, and those go directly in the cylinder. Okay, so two differences. The positive of each, the port fuel injection, it's easy to get to, it's easy to service. It's been tried and true for like 30 years or more. And generally, they're fairly efficient, and that fuel cleans the back of this valve. The direct injection is a little bit better because we don't have any leftover fuel right here, because we're spraying the fuel directly into the cylinder. Cool. So for efficiency, the direct injection is more efficient, but we're spraying it directly in the cylinder. We have compression in there, right? Like 180 PSI, 200 PSI. So if you're running port fuel injection at 55 PSI and you go to spray it into 200 PSI, what happens? Compression is just going to blow right back into that fuel system. It's not going to spray. So if you want to run direct injection, no problem. Run an injector down here directly in the cylinder and run it at 5,000 PSI. Have a nice day. Right? So that's why the direct injection systems are much higher pressure. They're going to have a mechanical driven pump. 22,000 PSI on some of the diesels. You can have at it. So more money, definitely a lot more design, but there's quite a few advantages. This is going to be more efficient. It's going to be better for power. The direct injection is a good way to go. There's one problem. In this, I'll make it generic and then I'll make it Toyota. This intake valve is going to be plunged into that combustion chamber where there's might be a little bit of carbon, a little bit of oil, a little bit of fuel maybe, but not a lot. It's going to collect it, and then it's going to come back up and cool off, and that's going to really build up a lot of carbon on that intake valve. And remember, we eliminated the port fuel injection, so that intake valve is going to get a carbon buildup today and a little more tomorrow and a little more next week and the week after and next month and the month after that. And then what happens? That intake valve's all sorts of carboned up to the point where air will try to come in, and this intake valve is so carboned up, it's restricting the air. And when it opens, the air and fuel that are in there are getting absorbed into the carbon, causing all sorts of issues. So if it's direct injection only, we'll more than likely need to come in here periodically and do like a top end clean, walnut blast it. Sometimes you can do like a BG 3-part cleaning and clean those up. There's different services that we could do. Now, why do you think you're not hearing a ton about this in Toyota land? Because Toyota runs direct fuel injection and kept the port fuel injection for a maintenance for the intake valves. You have a whole set of port fuel injectors and a whole port fuel injection fuel system just to maintain the intake valves from getting carboned up. Make sense? So more money, but less maintenance for the consumer and less breakdowns and stuff. Okay, so Toyota's got both. It's dual, direct and port. Cool. Now, as we follow the air is going to go to this intake valve. That intake valve, let's say in compression and power or combustion, should be closed, right? Well, assuming the timing is right, like we didn't jump a timing belt, or in this example is a little more simple. This is a timing chain, right? This is a basic timing chain. I'm a small block, Chevy. This is, don't worry, it's going to be fine. In fact, I can reach it. Okay, this is the most basic timing we got. These are so easy to line up. You just make the marks line up. It's really simple. But if you get into like more modern vehicle with this type of cam, you're going to have a timing chain going all up over the place, right? So assuming your timing chain or belt is correct, that means your camshaft timing is right. On your compression stroke, your valve will be closed. But what if we were to have like a damaged intake valve or a seat where the valve closes is the seat? What if we were to have a leak right there? What would happen when we're trying to make compression? Right, it's compression's going to push back out into the intake. And so we're going to either lose power or maybe even have a misfire right there, right? So that's kind of the direction we're going. For now, we'll just make sure you understand all the moving parts and pieces. Cool? So intake valve. Intake valve is opened by this thing. What do you suspect this is? Which one? Intake cam, which means this one over here would be, you know how I knew? Because the injector's on this side, so I know this is the intake. Also, the intake valves are a little larger, and the exhaust valves are a little smaller, and they also go to the exhaust manifold, and so therefore you can look right above and tell which is the intake and which is the exhaust cam, okay? You don't need to like look up service info to tell which one it is. You can look at it. You should know. Fair? All right, cool. So you got the intake and exhaust cams, intake and exhaust valves. What are these coily looking thingies? Oh, valve springs. Thought I actually had one over here, but I don't know where it's at. So yep, we got valve springs, and they have a few more pieces on there, retainer and stuff like that. This one does have a rocker arm, looks like right there. And this actually does have a hydraulic lifter right there, right? So they could vary. Then if we get into the block part, we've got the whole cylinder. The upper part will be the combustion chamber. We got a piston pin or a wrist pin, and that's going to connect it to the connecting rod, right? So there are all those pieces, pretty easy to see. On top of the piston or installed on the piston, you know there's some rings, right? So compression, oil rings. Sometimes they'll say number 1 compression, number 2 compression, oil control. They might have slightly different terminology, but you got some rings on there. Those are going to help seal the piston to the cylinder. So when we're on the compression stroke, this one's up Rotseni's alley, we should have a good seal between the piston and the rings and the cylinder wall. So when this is going up, it should be pretty airtight as it pushes up. But what if we had worn rings? It would. Where? It would go around. It would go around, and that's kind of like blowby, right? And if the compression goes around, then when we're on intake, guess what's going to happen? And when we're on power, guess what's going to happen? The combustion chamber, which has little droplets of oil, is also going to go around as blowby. And what's it going to leave on the liner, on the cylinder? Probably oil, yeah. Oil is going to be on there. So you're going to have oil consumption. You're going to have low compression. You're going to have oil consumption. And what do you think the fix is? Maybe rings, if it's truly the rings. You know, like me and the mad scientist got to tear apart the block to replace the piston rings you fried. Like, we could do that. But are you sure it's the rings? Because what if the cylinder's worn right here? That piston's gone up and down a bunch of times. What if the cylinder starts to get worn out? What if that cylinder was a 3.5-inch bore, and now it's a 3.5000-inch bore, and now it's a 3.5005 or 3.505? That'd be like it's worn out 0.005 of an inch. So like if the cylinder wears, you're going to put rings on it, it's going to fix it? What's going to fix it? Yeah, so then we get into, in Toyota, we don't bore these over. You got to get a new block. On some manufacturers, you can bore it over, then you can get a bigger oversized piston, oversized rings, or whatever. But the first step is determining, why is it consuming oil? Is it worn rings? Is it a worn cylinder? How do you think you're going to tell? The tear down. You're going to need to tear it down. We ain't sending nothing to the machine shop. You are the machine shop in this class, Sonny. Now, if it needs to be machined, we'll send it to the machine shop. You do the diagnosis. The machine shop people, a lot of times, not all the time, make less than the technicians. So you know, like, you got to be the brains behind the operation. Be like, hey, I'm sending this to machine shop. This is the measurement that I got. You know, you don't want to just send it blindly, because honestly, if they screw it up and then you put it in, it's still messed up. Your boss is going to be coming to you being like, hey, what happened? You'd be like, I don't know. And the more often you can say, I don't know, the less money you're worth. Makes sense? So you want to really know what's up and say, well, you know, this engine, for example, had excessive cylinder wear, so that's why it needs a short block. Or this engine didn't have excessive cylinder wear, it was just rings, and that's why it needs just rings. Now, you guys probably aren't going to rebuild a lot of engines, but maybe some. Maybe some. Makes sense? All right. And then the connecting rod right here, like I was showing right here, connecting rod. And then a little detail, these connecting rods, here's the cap, have bearings. This is the bearing. This is the infamous rod knock cause right here. If this bearing gets worn, you get you know, that's how I blew my bike up. My bike got a rod knock. Cool. So if I were to bolt these together, this is going to go around the crankshaft, and this torque spec is very critical. And ooh, it's all right. This one's going in the trash anyway. And these bolts are torque to yield, and the exact clearance between the bearing and the crankshaft, we'll need to measure that at maybe like 1.5 thousandths of an inch oil clearance. Like, this is very delicate, fine, detailed work. You don't just slap it together in the barn. Make sense? So like, when we get into this, you need to be really careful about your measurements. I know about good and tight. I know about Milwaukee torque. I know about all that. That is not at all in any way the place to, if it fits, it ships. Like, that's not, no, those won't last. All right, so that's going to be detailed stuff. We're going to get there. All right. So there's a bit of your bottom end, and we cover the bottom end. So you guys know the top end and head is a whole lecture, and the bottom end and block is a whole separate lecture. Okay, this is just the overview of how they fit together. Now, I told you we were going to cover this in more detail. It's kind of review, but this is where we're really going to dial it in. You ready? The intake. Tell me what's happening there.
Air entering.
All right, what's the piston doing? Piston's going down. Intake valve should be open. It hits BDC. What happens? Intake valve closes. So no valves are open, right? That makes sense because this is on its way up. If you want to build compression, you can't have a valve open, right? Compression gets to TDC. What happens? Spark, right? And then that's going to actually start to combust, burn the air and fuel. Now, the fuel was already in there if it's port fuel injected. If it's direct injected, sometimes they don't spray the fuel till the last second. They do all sorts of crazy stuff with direct injection fuel systems, right? But either way, it's air and fuel. We spark it. It starts to build pressure, pushes down. That's the power stroke. Then BDC, it does what? Comes, exhaust valve opens, and this comes up, and it is going to push all the air out. That's exactly it. But one of the things I like to point out is, if you were to look at the crankshaft's actually at top dead center twice. It's top dead center compression, bottom dead center, top dead center of where the exhaust stroke is ending, right? So when you go to TDC, you got to make sure, if you're looking for top dead center compression, it's where this is at top dead center and both the valves are closed. If this is at top dead center and the exhaust valve is open, that's top dead center of exhaust. That's different. Make sense? That's one of the things I want to make sure everybody gets. Because I've seen a number of people say, yeah, I set it at top dead center, but the exhaust valve was open and they thought that it was top dead center compression. Okay, go ahead. Yes, and I can even step that up another notch. If I were to have you looking at this, and let me see if actually it does have a mark on the cam, because it doesn't always. Well, it does, but sometimes it's hard to see, I guess is what I'm trying to say. Oh, it's got one. I'm going to make a couple marks on this, and then I'm going to show you something that I think will really help. Because yes, there are There are marks, but you got to know exactly what you're looking at with the marks. Okay. Exactly. Exactly. Ooh, that was really close. I just need one more tooth over. Okay. All right. What color you want to put on here? I'll tell you what, I've got something called Prussian blue right here. And this Prussian blue is something that we're going to end up using in class to do a number of things. So I'm going to put a little dab of Prussian blue here and here. Then I'm going to bring it over to the camera. And I want you guys to all get to see it. Okay. Okay. This should immediately show you the camera. Okay. Now, when I bring it over here, all right, technically, let's see it with, is the light helping or making it worse? Let's see. All right, maybe we need just a little more light in my face so I can't see. Can you guys see those timing marks are lined up? That's generally going to be your TDC compression. Now watch when I turn this. This is upside down. This is actually the crank and this is the cam. But I think it's going to be easier because this cam's kind of heavy to hold it upside down. Watch when I turn this. All right, and remember the crank is on top in this case. Watch when that mark comes back down. I don't think I wiped the mark. Oh, look at that. You see that mark? So that's on TDC, right? Why isn't there a mark on the cam anymore? Right, so it comes, the crankshaft will go to TDC twice. This would be the wrong TDC. You want to see the right TDC? I got to turn it another 360. Oh, that's TDC compression. The other one was TDC exhaust. And that gets people pretty messed up. You'd be actually kind of surprised. Okay. Uh-huh.
So say like you do like pressure test at exhaust TDCs and you get like a low pressure rating, that's all even engine.
I'll bite on that too. Let me get my screen share back up. I lost my Zoom controls. Where's my Zoomy controls? Are they up there? Oh yeah, they were up there, huh? Where's my Zoom? Okay, I need to start the share over. Screen 2, share. Okay. When you go to do this, you just want to be aware of where it's really at. And if you think about this, you won't get confused. When we do a compression test, we're cranking it. We're not worried. But if you go to do a cylinder leakage test, yeah, you're going to think it's failing. Sometimes the way I cheat is if I just inject air in the cylinder and it seems like it's leaking a lot, I'll just turn at 180. Like I'll do it sloppy. Let me show you that when we actually do the cylinder leakage, how I would personally do it to make sure you never mess that up.
Yeah,
I know what you meant. Yeah. It's okay.
So when you do smoke test, you want to do it.
We don't normally smoke test an engine, but if you were to try to do a various number of different tests that require top dead center, yeah, you're definitely going to want to make sure you're truly at top dead center. And then, oh, you know what, you guys, I got to start this, but my computer's being kind of a pain in the butt. It's interesting. I lost my control of my second screen. Let me figure that out 1 second. It's really mad at me. Very mad at me. Okay. Give me just a moment. Okay, that should work. Okay. You guys check on Canvas, on Zoom, you see the right screen right now or no? I killed the share, huh? Okay. Now you should see the correct one. How's that? Like it? Okay, very good. It's just weird. There we go. All right, so on that intake, you guys can see piston down, intake valve opens, air comes in, all right? Compression, what should the status of the valves be? Closed. Makes sense? Now, if we were to do it down and dirty, if you're looking at those marks and you couldn't exactly tell, you can also look under the valve cover and see if the point of the cam, like this, is up away from the valve, then that valve's closed. Then if you rotate it down and the point of the cam pushes the valve down, then you know that valve's open, right? So if it's at TDC and I want to know if it's at TDC compression or TDC exhaust, I'll look at the exhaust cam, and if, let's say, I'll make it this cam right here. If it's like this and the valve's down at the bottom, we're good. But if I see it and it's down here and I can see that the cam is pushing on the valve, it's like, no, I got to go another 360 and then it'll be up here. Because remember, 360 on the crank turns a 180 on the cam. Roxanne, go ahead. Exactly, but that's coming up. All right, so if you look at this, there's your compression, and then here's that measurement of the stroke, right? TDC to BDC is going to be your stroke. And then right here's the calculation of the displacement. Like we jumped the gun a little. That was me getting excited. But in reality, you're going to look at the bore of 3.550 and a stroke of 4.160. And you're going to do displacement equals bore squared times the radius of a fourth times stroke. That part's a little bit weird. I didn't think that was the calculation, but that's the engineer's calculation. Would we calculate it? Probably not. If you like to do those types of things, that's going to be more engineering. Like the customer's never going to come in and be like, hi, can I see your math on the calculations for my displacement? The customer's going to come in and going to say, hi, my check engine light is on. Check and advise. And then you're never going to be like, well, let me calculate the displacement really quick, you know, but you still do want to understand this is what the engineers would do. Cool. So that's how they get that number. So just for fun, you guys know what a 2-liter Mountain Dew looks like, right? Yeah. All right. If it's a 2-liter engine, all your piston displacements combined equal a 2-liter. So back in the day, people would be making fun of you. You had a 1.6. They'd be like, oh, bottle of Mountain Dew's got more displacement than your Honda. You know, we've heard it all. Okay. Then you get into the V8s, you know, what's the Tundra V8 displacement? It could be the 4.8 or the 5.7 or, you know, or 4.7 or the 5.7. And so, oh no, here we go. Okay. 6.7 would be like a Power Stroke diesel, right? So those are all the displacements, right? 6.7, 5.7, 4.7, that's liters. 5.7 translates to right around 350 cubic inches for your own reference. So when you hear 350, that's about a 5.7. You hear a LS2, that's a 6.0, 6 liter. You hear LS3, that's like a 6.2. My favorite LS engine personally is the LS7. You guys ever heard of it? 7 liter, 427. America Power. It's a that's a unit right there. That's a good one. Okay, but you could buy bigger engines, 572s and whatnot. That's 572 cubic inches with all the cylinders combined. Okay? You got something to say, huh? What about it? We don't use 4-letter words that start with F in this class. I hear nothing about no Ford. No, the 5.0 is fine. Yeah, exactly. So now when you hear these numbers, you know what they mean. It's all the displacement of all the cylinders. If it's motorcycles, it's the displacement of all the cylinders, but in cc's. Now let me tell you what I used to work on, locomotives. I think I told you guys that, right? I'll share some pictures with you sometime, maybe not right now. I should have actually put them in the presentation because I had some cool pictures. A piston and rod on a locomotive would be right here if it was sitting on the ground. One of them would be this tall from the ground to me, 4+ feet tall. So I remember there was a guy with a big old Cadillac with like a I don't remember what it was, maybe a 496 or something, some big old Cadillac. And the road was closed because there was a thing with the train. And so they're stopped. And he's talking with the guy who worked for the railroad company. And he's like, you know, what engine's in there? And they're like, that's an EMD. It's a, man, it's been a while since I thought about it. I have to think of the names. 572. I'm actually going to have to cheat. I haven't thought about this in a long time. EMD, they give you the engine size. EMD engine displacement. Oh, a 710. Yeah, like a 567. Let's do a 710. So it's a 710 displacement, 710 cubic inches. Cool. So this guy's like, well, mine's like a 496 or something. Like that locomotive's only a 710. That tells you the Cadillac engine's big, right? You want to know what the engineer didn't tell him? It's 710 cubic inches per cylinder, and there's 16. So, you know, like a Cadillac with a 400 something cubic inch is cool, but a locomotive with 710 cubic inches in one cylinder, and it's not a V8, it's a V16. I mean, there's displacement beyond displacement. You know what I'm saying? So pretty cool. I got some pictures, right? So now you guys know all about displacement. Makes sense? So if you guys are going to rent, go out in the desert and rent an ATV, and you say like, hey, do you want the 250EX or do you want the 450ER? What are you going to say? Like, give me whatever the biggest number is. More displacement. Makes sense? That's what I would do. Okay? Cool. And then you guys can see kind of what that looks like. Here's your bore and stroke, and then it's going to be for all the cylinders. Cool? Now let's talk about compression. All right, check this out. This is your combustion chamber at TDC, right? So if you were to measure that volume, and then you were going to go to all the way to BDC and measure this volume, that'll give you your ratio. If you have 8, whatever the volume is, to 1, whatever the volume is, that's 8-to-1 ratio. Does that make sense? Kind of, sort of. All right, so how would we improve our compression ratio? Well, if you had, think about that for a second. If you had a shorter rod, it would come down further, but then when it goes up, it wouldn't squeeze it all the way to 1. So that alone won't do it. Basically, what you'd have to do is have to either make this bigger without making the combustion chamber bigger, or you know what we normally do, to be honest? We'll make this smaller. So like if you were to take a cylinder head and put it on a machine and cut 10 thousandths off it, or 20 thousandths, or 30 thousandths, you made the area of number 1 smaller. So it'd be almost like, let's say you made this number 1 into like a 0.9. What if you had an 8 to 0.9? That's actually going to be more than an 8-to-1, right? An 8 to 0.9 is a higher compression ratio. We normally make this combustion chamber a little bit smaller to change our compression ratio if we're trying to modify it. Now, what the engineers would do, yeah, they could just change this stroke and bore, and you know, they do all that type of stuff from the ground up when they're designing the engine as part of their engineering design. Make sense? 8-to-1 is a very outdated compression ratio. We're not doing them like that anymore. That's just not going to be that efficient. But it would run for a long time, and you wouldn't have to fix it, and it's going to have an easy job. It's just not going to have good efficiency, good fuel economy, and very good emissions. Cool. And so again, that's kind of what it's talking about, the 8-to-1. It would be affected by the size and shape of the top of the piston. So like, for example, this is a flat top piston. What if you were to put a little dome on it? Hemi's a little different, but you might have like a wedge or a dome on top of the piston. That's actually going to increase it because, yeah, this space up in the head was a 1, but now it's a 0.9. And then technically this space down here is reduced a little bit because of the wedge, but this space up here is reduced a lot, and this space reduced here a little. So you'd increase the compression by putting a dome. What if you wanted to build a car to run a lot of boost? Because if you run big boost, you're increasing the compression, but not the compression ratio. Make sense? The fact that you're pressurizing the air is going to make more pressure, but it's not affecting the compression ratio. If you're going to run big boost, you might want to lower your compression ratio. You know that? So what kind of piston would you do? Like not a dome, but like a dish piston. Yeah, like a concave piston. They'll call them dish pistons. That'll actually be kind of like drop down in the middle. That'll lower your compression. The reason you'd want that is so you can increase your boost without exceeding, you know, without having too much cylinder pressure, or without having such high pressure that you need to run like E85 or high octane fuel. Maybe you want to run E85 anyway, don't you? You ain't going to get no range though. From the factory, they don't want to have you forced to run E85. Make sense? So they'll lower the compression a little bit. Yeah, that's what I'm saying. Right, cool. So they figure some of these stuff out. There's a tricky thing that we can do, altering the valve timing. And this one, I don't want to totally blow your mind on the first day, but you guys have heard of Atkinson, right? On an Atkinson engine, what they'll do is extreme variable valve timing, and they'll leave the intake valve open while the compression's coming up. So if your compression's coming up and your intake valve's open, it's all bleeding out into the intake, right? So you're lowering your compression. And they want to do that because if you leave it up halfway and you have a 1.6 liter, but you leave it open halfway, you basically bled off 0.8 liters and you only really have a 0.8 liter. That's going to be good on gas. That's not going to have a lot of power. But we don't really need a lot of power because a lot of them are going to be hybrid, or, you know, we're going to do it on the freeway for efficiency, right? So you get crazy about doing variable valve timing stuff. You can mess with compression too. Cool. So overall, that's pretty good. Now, when we talk about timing, you guys have heard this before, but I want to make sure I'm really clear on there's two types of timing, okay? So when I say timing, I might not always say which timing I'm talking about, so you have to understand perspective. If I'm talking about the cam and intake and exhaust and stuff, and I say timing, I'm talking about camshaft timing. Camshaft timing, any adjustment for that will be up in here, right? This sprocket, this chain is all going to be the same, but I'm going to actually advance or retard the timing with oil in this VVT controller, phaser, if you will, right? I'm going to move it. That's going to change where these lobes are. I can open the intake valve early. I can close the intake valve late. I can open the exhaust valve early. I can even have the intake and the exhaust valve overlap a bit. So that way, when the exhaust valve opens and it's pulling the exhaust out, sometimes it'll even scavenge and pull a little bit of fresh air a little bit further, and that'll give us a little closer to that 100% volumetric efficiency, right? That's all valve timing or cam timing. That's mechanical, cool? This is not. This is talking about ignition timing. The ignition timing all has to do with when the spark plug fires. Does that make sense? Now, you would assume you want your spark plug to fire right at the top, TDC, right? Because that's what I've been telling you so far, but that wasn't accurate. We actually need it to fire before TDC. And the reason why is because it takes time. When you spark the spark plug, it actually takes time for that flame to travel and to build pressure to push the piston down. All right, so this is how I think of it. Who's ridden the bike before? If you've ridden a bike, you'll understand this. If you haven't, there's something wrong. All right, when you pedal like this, right? Let's say you're with this foot, right? And it's coming up to the top of up to the TDC, cool? This is TDC. When it gets to TDC, you already have to start starting to push down, right? Because it's going to take you a second to really engage it. So if you don't start pushing down until it's at TDC, by the time you really catch it, it's already part way down, right? So do you get a very good push if you start kind of late? So you lose power, am I right? Wouldn't you assume if you start your push down a little bit late, you're catching up to the pedal and you lose a little bit of power, you don't get a real good push. You lost horsepower. So what we really do is we actually start the spark a little early so that the flame builds maximum pressure right as it passes TDC and gets a real good, thorough push. If you guys have kickstarted a motorcycle, you know what I'm talking about. You got to start way up at the top and get a good push on it and you'll start it. New people are kind of like, they're wasting half the kick and they just get a little thing at the bottom. It's like, that ain't going to work. Try again. Buy an electric start. You know what I'm saying? So like we started early. So when we're talking about timing, it all comes down to degrees, right? We don't say start at a second early. You say start at a certain amount of degrees early. For example, maybe 10 degrees or maybe 20 degrees, right? It could really vary. So let's just say at idle, we're probably going to do about 10 degrees before top dead center because it's going kind of slow. So when it's almost there, we'll do the spark. The flame will spread. By the time we're just passing TDC, the flame is pushing down. Cool? Try that at 6,000 RPM. Even in this case, 2,500 RPM. Because it takes 3 milliseconds to reach the maximum pressure. So at 2,500 RPM, you know what we should do? Should we start it earlier or later? Even earlier because it's going faster, right? So if we started earlier, that'd be like 20 degrees before. Make sense? 0 is right at, 10 degrees is a little early, 20 degrees a little earlier, 30 degrees is really early. Make sense? So like some cars, you know, they come kind of conservative on how early it is, right? So now picture that top dead center thing. If you start at 10 degrees sooner, you're going to get a pretty good push, right? But if you're going really fast and you start at 20 degrees sooner, you're going to get a good push. What if you pushed it to 30 degrees sooner? You might either A, get an excellent push, right? You just gain horsepower without changing any parts, just the tune. You go in the tune and you change it 20 to 30 degrees before top dead center. And all of a sudden you're like, ring, bang, bow, bing, bang, ow, B-Tech, bing, bang, B-Series, no? Right? You get like all that stuff. Or that would be the good. Or what happens if it's too soon? Picture it. It's coming up and you're like 30 degrees before top dead center. And it's like, I'm not ready for that. And it tries to push it backwards. How do you think your piston and its bearings are going to like that? Here they go coming around and they're like, all right, I'm ready to go. And then it's like a little too early. It tries to shove them back. This is going to slam in the crankshaft. You're going to nuke the top of those connecting rod bearings. If all the tops of these connecting rod bearings are totally destroyed, that timing was too advanced. Make sense? It's an ASE question, actually, just so you know. Cool, but you're just going to follow this. Yeah, exactly. You're just going to follow kind of what I'm saying. The ignition timing has to do with when the spark starts, and you want it to be a good push, but if it's too early, it'll try to push it backwards. And Roxanne, you've experienced this? If you have a way to adjust timing, sure, but you don't. If it's a distributor, we could literally adjust timing by turning it. But on a modern car, you have to get a tuning program. My HP tuners doesn't work on Toyota. You can't do it. Cool. All right. And then when we talked about the rotary, I think you guys will get that when we do the discussion a little bit more. Now let's talk about the engine layouts. Inline, everybody's good with, right? Inline front to back. Give me an example of an inline engine. The 2JZ. Oh, the 2JZ. The 2JZ. You got it. 1, 2, 3, 4, 5, 6, right from the front to the rear. Inlines are always easy. V's are different. So here's a V. By the way, I could give you a really fun assignment, but I'll just talk you through it to save the time. If you look up, let's say it's a 4Runner, and you need to know what cylinder it is. You got a misfire in cylinder 1. Is it the driver's side front or the passenger side front? True, but which one? So you have the even bank, like in this one, the even bank is on the passenger and the odd bank is on the driver. So cylinder number 1 is the driver's side front, right? You can tell by that diagram. But look at this one. This one's sideways, transverse, so that's like a Camry or something, right? So if I don't know, or a Sienna or exact, to be honest, I don't know every car. I really don't. I used to, because they used to be the same. Then they started switching up. So back in the day, GM, the number 1 was always driver's side front, and I always knew. Then all of a sudden the 3.6 came out, and you'd have a cylinder number 1 misfire, and you'd be working on the driver's front. You'd be like, you're not even on the right cylinder. It's now the passenger front. Why? I don't know. What all comes down to, if you look at the engine, it's what rods are installed on the crankshaft in order. So a lot, like on this one, the front cylinder is set a little far forward. Can't you tell? See how the front one's a little far forward? This one has a rod, then this rod, then this rod, then this rod, and so on, right? But if you look on this one, number 1 is actually more like the passenger side if it was front over here, right? So this is what's crazy. On a 4Runner, if it's a V8, it's the driver's side front, and if it's a V6, it's the passenger side front. Cylinder 1 is in different spots on different engines. So this is what I'm saying to you. If you don't know, look it up, because it varies engine to engine. It varies even car to car. Why? Just like I said, for whatever reason, when they designed it, they decided cylinder 1, bank 1 is going to be on the right side, whereas it used to be on the left side. I don't know. Now, when we say right and left side, it's always from the perspective of if you were to lift the body of the car off and jump yourself like this, and jump right up on that transmission, and you are looking at the front like this, it's always from that perspective. It's never how you work on it. You don't open the hood and be like, that's the left. No. You got to like this, and look like this. Now, you know why I'm making the sounds, right? Because I don't want you to forget. So I do stupid stuff when I want to make sure you remember. Now, remember that, huh? You can even do it. So when you pop the hood and you're not sure which one it is, do this. And then people from the other cohorts will be like, I'm still doing that, huh? You can. Yeah, you might get kicked out. But it's okay. All right, and then let's say you're trying to figure out what the engine is. Here's a little bonus. On a lot of Toyota stuff, there's some numbers stamped in there. So if you're trying to determine what the heck it is, I mean, you could look at the VIN, you could pull a VIN or whatever, but if it's not in the car, there's going to be some numbers. This one, for example, says 3UR. Then it says some other blah, 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 blah. And this gets into some of the more of the details of, you know, if it's a 1GR, it's down here. If it's a 2UZ, it's back here. If it's a 3UR, it's in the front. You know, it's where it's at could be different. For a lot of manufacturers, it's going to be similar. So like if it's a 5.3, they'll have it back here on the cylinder. If it's a 4.8, it'll be back there on the cylinder. You know, if you're really going to do this, you want to be able to identify what engine it is separate from the VIN. Cool. Now let's break down what it means. This is a fun question I got in the past. Somebody asked me, why is it a 2JZ GE, GTE, GE and GTE? All right, well, let's start with the basics. FE, almost everything you're going to see is FE, fuel injection. Electronic fuel injection. And the E is the electronic, but the F is a narrow included Valvetrain angle. You're like, what? Narrow included. Okay, you ready? You guys have seen this dance. Ready? Not the YMCA. No. Narrow included, wide included. Narrow, wide. Okay? So if the valves are like this, that's narrow. That's normal. The wide is actually really cool, but if it's wide, think of how big that head's going to be. That head's going to be huge. If you ever look at a 2JZ GTE, it's like it's a beast. So you got the intake, and it's kind of a flatter path. So it's easy to have the intake flow in. It stays kind of flat, does its thing in the cylinder, and comes out kind of flat. It's good for flow. It's high performance. But, you know, in a Camry with the V6, we don't have room for a big head like that. So we're running narrow inclusion. FE is going to be the generic, the more common, I should say. GEB wide. What if it's a GTE? It's a wide inclusion turbocharged. That's the one you want, right? So now you know why. You might see a Z, that'd be good, but not like the 1ZZ or the 2ZZ. It'd be like a FZE. If you had the X, okay, who's been hearing the X a lot? They kind of changed it. What are you guys hearing now? FKS, huh? All right, so FKS is going to be, this is actually a little out of date. FKS is going to be direct injection and Atkinson cycle. So they went away from the X and went to the K. Okay. FKS, isn't it? FKS is Atkinson, direct injection. I don't remember, and I think it's just because the F is still narrow inclusion. T makes sense, turbocharged. X is Atkinson's, but I think K is too. Yeah, yep. So why they changed it, I don't know. They didn't really update any of this, though. They changed it, but they never really put out a ton of info. Cool. And then when we talk about number of cylinders, I think you guys are probably pretty good. I think right now is actually probably going to be pretty good. You guys feel like you want to take a little break? All right, so let me do a little pause here. I should have told you to bring your